Opening. Every answer from artificial intelligence begins somewhere far from the screen, as a small movement of electricity through a very large machine. Tonight, we will follow that movement from a power station, across the grid, into a liquid-cooled rack of processors, and finally into the heat that must be carried away. Along the way, we will discover why each AI task is becoming more efficient even as the whole system asks for more power. There is no need to remember every number. The important thing is the shape of the journey. When you type a question into an AI system, it can feel as though the answer comes from nowhere. A blank box waits, a cursor blinks, then language appears. The screen does not show the transmission line outside a power station. It does not show a substation changing voltage, or a transformer humming behind a fence, or a pump moving water through a metal plate pressed against a processor. But all of those things are part of the answer. In 2024, the International Energy Agency estimated that data centers used about 415 terawatt-hours of electricity around the world. That was roughly 1.5% of global electricity consumption. It was still a small share of the whole system, but it was already large enough to be measured in the same unit as the annual electricity use of countries. In the IEA's central projection, global data center demand approaches 950 terawatt-hours by 2030. This is a forecast, not a promise. Efficiency may improve faster than expected. Construction may slow. New applications may grow more quickly. Yet the direction is clear enough to change how technology companies, utilities, and governments think about electricity. The most interesting part is not simply that AI uses energy. Every useful machine does. The interesting part is the contradiction inside the trend. A simple AI task can require far less energy than a similar task required only a short time ago. Hardware becomes more efficient. Software learns to avoid unnecessary work. Models become smaller or more specialized. And still, total demand can rise. More people use the systems. They use them more often. A short text response becomes a long chain of reasoning. A single image becomes a generated video. A chatbot becomes an agent that works for minutes or hours. The energy needed for each step falls, while the number and ambition of the steps grow. So tonight's story is not a warning that every question is wasteful, nor is it a promise that efficiency will solve everything. It is a quieter story about scale. It is about the physical world hidden behind digital intelligence. If you are listening in bed, you can let the details drift past. Imagine one small unit of electrical energy beginning its journey toward a distant machine. It has no idea that it will soon become part of a sentence. It simply follows the path that the grid provides. Chapter 1. Before the data center. Long before electricity reaches a processor, it begins as motion. Water turns a turbine, wind moves a blade, steam expands through machinery. Sunlight pushes electrons through a solar cell. Natural gas burns. Uranium atoms divide and release heat. Deep underground, geothermal energy warms fluid that can be brought toward the surface. These sources are different, but the data center does not receive a separate kind of electricity called AI power. It receives electricity from a grid, a vast, shared system in which generation and demand must remain in balance from moment to moment. This balance is easy to overlook. Electricity is not delivered like a parcel that can wait in a warehouse. Batteries can store some of it. Reservoirs can store energy as elevated water. Fuels can wait before they are burned. But on the grid itself, supply must continually respond to demand. Imagine a quiet control room at night. Operators and automated systems watch frequency, voltage, weather, generator output, and transmission constraints. Most customers appear as many small variations blended together. A kettle switches on. An air conditioner pauses. A factory changes shifts. A large data center is different. It may ask for tens or hundreds of megawatts at a single location. A traditional facility might draw between 10 and 25 megawatts. A hyperscale AI site can exceed 100 megawatts. The largest projects discussed today are larger still. 100 megawatts is not a measure of energy over a year. It is a rate, a continuous appetite for electrical power. If the facility runs near that level day and night, its energy use accumulates with every hour. The grid must therefore answer a practical question before the AI system can answer anything at all. Can enough electricity reach this place reliably? That question can take years to resolve. A location may have land, fiber connections, and access to customers, yet still lack a strong enough electrical connection. New transmission lines require planning, permits, equipment, and construction. Large transformers are specialized machines with long supply chains. Substations need space. Generators need fuel or favorable weather. Communities need confidence that the new load will not reduce reliability or raise costs unfairly. This is why the geography of AI is partly a map of electricity. Data centers gather where fiber is available, where land and water can be managed, where taxes or planning rules are favorable, and where the grid can deliver firm power. The United States, China, and Europe contain large concentrations of capacity, but even within those regions the load is clustered. A global share that appears modest can become a major local issue. The IEA has estimated that, without action on grid constraints, around 1/5 of planned data center projects could face delays. A projection like this is uncertain, but the mechanism is straightforward. Software can be copied quickly. Electrical infrastructure cannot. This difference in speed shapes the entire industry. A model can be improved in months. A new application can reach millions of users in days. But a transmission corridor, a turbine factory, or a new nuclear reactor moves on a different clock. AI develops at the speed of code, while its energy system develops at the speed of steel, copper, concrete, law, and geography. Our small unit of electricity has not yet reached the data center. It is traveling through high-voltage lines because high voltage allows power to move over long distances with lower losses. It passes through transformers that adjust voltage for different stages of the journey. It joins a flow created by thousands of generators and millions of customers. Somewhere ahead, a substation waits. Chapter 2: The Gate Between Grid and Machine. A data center begins, in electrical terms, at its connection to the grid. The connection may include multiple feeds so that one failure does not stop the facility. High-voltage equipment protects and isolates parts of the system. Transformers reduce the incoming voltage to levels that can be distributed through the campus. Switchgear directs power. Meters measure it. Protective relays wait for conditions that should never occur. Reliability is designed in layers. If grid power disappears, batteries or other short-duration systems can respond almost instantly. Backup generators may start and carry the load for longer. These systems are not merely conveniences. A sudden loss of power can interrupt work, damage data, or leave equipment in an uncertain state. The data center is therefore not a simple building with a very large electrical socket. It is a small electrical ecosystem. Power enters the site, changes voltage, moves through distribution equipment, and eventually reaches rows of cabinets. At each stage, a little energy is lost as heat. Engineers track the relationship between the total electricity entering the facility and the electricity delivered to computing equipment. One common measure is power usage effectiveness, often shortened to PUE in its simplest form. It compares total facility power with the power used by information technology equipment. A value close to 1 means that relatively little additional energy is being used for cooling, lighting, pumps, and conversion losses. Real facilities never reach a perfect 1, and the number must be interpreted carefully, but it reveals an important truth. Not all data center electricity performs computation. Some of it moves air, some moves water, some passes through equipment that protects the system. Some is lost each time power is converted. The computer is surrounded by machinery whose job is to keep the computer supplied, cool, and stable. For years, data center efficiency improved enough to offset much of the growth in digital activity. Servers became more capable. Facilities consolidated work into efficient hyperscale buildings. Virtualization allowed one physical machine to do the work that had once required several. AI changes the shape of the load because it favors dense clusters of specialized processors. These processors do not work alone. They require high-bandwidth memory, network switches, storage, central processors, and fast links between machines. The purpose of the cluster is to keep valuable accelerators busy. An idle processor may still consume power, while a processor waiting for data wastes both time and expensive capacity. So the facility is designed as a chain. Electricity must arrive. Power conversion must remain efficient. Data must arrive at the processor. Results must leave. Heat must be removed. If one link becomes a bottleneck, the rest of the system cannot reach its potential. This is also why data centers prefer continuous, dependable electricity. A large training run may coordinate many processors for days or weeks. An inference service must be ready whenever a user asks a question. Reliability is part of the product, even though the user never sees it. The source of that reliability can vary. Some facilities rely mainly on the existing grid and buy renewable electricity through contracts. Some support the grid connection with batteries. Some developers are exploring on-site natural gas generation. Technology companies have signed agreements connected to nuclear energy and geothermal projects. In regions with abundant hydroelectricity, flowing water may support much of the load. None of these choices is effortless. Solar and wind can be built relatively quickly and produce low-carbon electricity, but their output changes with weather and time. Batteries can shift energy and respond quickly, but duration and cost matter. Natural gas can provide firm, dispatchable power, but it produces emissions and depends on fuel infrastructure. Nuclear power is firm and low carbon in operation, but new projects can take years and carry financial and regulatory risk. Geothermal energy can be steady, but it depends on location and drilling technology. The future AI power system will probably be a portfolio, rather than a single answer. There is another part of the gate that receives less attention than the processor: the transformer. A transformer has no intelligence. It does not run a model or store a token. It uses changing magnetic fields to move electrical energy between circuits at different voltages. Yet without this old and remarkably durable invention, modern computing could not gather power from the grid safely and efficiently. Large transformers are not ordinary products waiting in unlimited numbers on a shelf. They contain carefully manufactured steel, copper or aluminum conductors, insulation, cooling systems, and protective equipment. They are heavy. They are often tailored to a project. Their production and delivery can take far longer than the installation of a row of servers. The same is true of switchgear, turbines, and power electronics. The AI supply chain therefore extends beyond advanced chips. It reaches mines, metal processing, electrical equipment factories, rail lines, ships, and specialist engineering teams. This wider chain explains why money alone cannot make capacity appear instantly. A company may be willing to buy power. A utility may agree that the project is valuable, but the required transformer still has to be manufactured. The substation must still be built. Protection systems must still be tested. A fault in a high-voltage system carries consequences too serious for improvisation. The IEA's 2026 analysis noted that the density of AI servers is testing supply chains for power electronics and transformers, just as rapid demand for gas turbines is creating another bottleneck. These constraints are less visible than a new model announcement, but they can determine when that model can be served at scale. In this sense, the data center has two clocks. One clock counts generations of silicon and software. The other counts factories, permits, and grid equipment. The future arrives only when the slower clock is ready. Our unit of electricity has now passed through the gate. It is inside the data center. Ahead are power shelves, cables, and bus bars. The scale of the journey is about to shrink from regional transmission lines to metal conductors inside a cabinet. Chapter 3. Inside an AI rack. From a distance, a server rack looks like a tall black refrigerator. Inside, it is a carefully organized vertical city. There are compute trays containing processors. There are network switches that allow processors to exchange data. There are power supplies, cables, and management systems. There may be storage devices and control computers. In the newest dense AI systems, there are also pipes and manifolds carrying cooling liquid. One documented example is NVIDIA's NVL72 rack. The name refers to a domain containing 72 GPUs connected through a high-speed technology called NVLink. The rack contains 18 compute trays, each with central processors and 4 Blackwell GPUs. It also contains switch trays, management switches, power shelves, a bus bar, and liquid cooling manifolds. This is one product architecture, not the definition of every AI system, but it shows how the basic unit of computing has expanded. The processor is no longer the whole machine. The rack itself becomes a coordinated computer. Power shelves receive electricity and convert it into forms the electronics can use. A bus bar distributes large currents through a rigid metal conductor. From there, electricity moves into boards filled with components whose features are measured in tiny fractions of a meter. The contrast is remarkable. Outside, transmission towers may stand higher than buildings. Inside a chip, transistors are so small that billions can fit on a piece of silicon held in one hand. The same physical law connects both scales. Electrical potential moves charge. Charge switches circuits. Circuits perform arithmetic. An AI accelerator performs enormous numbers of mathematical operations, especially the matrix operations used throughout neural networks. Yet arithmetic is only part of the energy story. Data must also move. Model parameters travel from memory toward computing units. Intermediate values are stored and retrieved. Results pass through networks to other processors. In many workloads, moving data can be as important as calculating with it. This is one reason high-bandwidth memory sits close to the accelerator. Distance, bandwidth, and energy are linked. A useful result must arrive at the right place at the right time. If the processor waits for memory, its theoretical speed does not matter. The rack is therefore choreographed. Software divides work across processors. Interconnects move information. Schedulers group user requests. Memory systems retain the data needed for the next step. Cooling systems respond to heat. Power management adjusts to changing load. From the outside, the rack does nothing dramatic. Lights blink, pumps hum, fans turn. From the inside, patterns of current change billions of times per second. By 2027, the IEA estimates that the peak power demand of an advanced AI rack could be comparable to the electricity used by 65 households. This is a projection, and it describes peak power rather than annual household energy. It does not mean every rack has reached that level today. Still, it captures the direction of travel. Between 2020 and 2025, according to the IEA, the power density of AI servers rose by about 11 times. By 2027, it could rise another fourfold. More computation is being placed into the same physical footprint. Density changes the engineering problem. A conventional rack might be cooled by pushing conditioned air through it. As power density rises, the volume and speed of air required become impractical. Heat must be captured closer to where it is produced. Liquid can carry much more heat than air through a smaller space. In a Grace-Blackwell rack, documented liquid loops connect to cold plates attached to major heat-producing components. Other parts remain air-cooled. The system is hybrid because no single method needs to serve every component. Our unit of electricity finally reaches a processor. For a brief moment, it contributes to a calculation. A transistor changes state. A number is multiplied. A value moves through memory. And almost immediately, the useful electrical energy becomes heat. Chapter 4. Why computation becomes heat. Heat is not an accidental side effect added after intelligence. It is what remains when electrical work has been performed. Inside a processor, transistors switch between states. Wires carry signals. Capacitors charge and discharge. Electrical resistance converts part of the energy into thermal motion. Even when no visible part moves, the chip is physically active. The result is a strange transformation. Electricity enters as organized potential. The processor uses that potential to create a temporary pattern of operations. The pattern may help identify an object, predict a token, or generate a frame of video. Once the operation is complete, most of the energy has dispersed as heat. Information remains. Heat must leave. If it does not leave, temperature rises. Electronic components become less reliable. They may reduce their speed to protect themselves. At higher temperatures, they can fail. Cooling is therefore not separate from computing performance. It defines how much computation can fit in a space and how consistently that computation can run. In a liquid-cooled system, a cold plate sits in close contact with a processor. Channels inside the plate allow coolant to flow near the hot surface. Heat crosses from silicon and packaging into the plate, then into the liquid. Pumps move the warmed liquid away. Heat exchangers transfer its energy into another loop or into the surrounding environment. The exact design varies. Some systems use water. Some use mixtures selected for temperature and corrosion control, Some immerse components in special fluids. Some use outside air when weather is favorable. Others depend on chillers. The word cooling can be misleading because the heat does not disappear. It is moved. From the chip to a cold plate. From the cold plate to liquid. From liquid to a heat exchanger. From the facility to air, water, or another useful destination. In some locations, waste heat can warm nearby buildings or support industrial processes. The temperature and distance determine whether this is practical. A large quantity of low-temperature heat is not automatically useful, but it can become part of a local energy system when the infrastructure is designed together. The share of electricity used for cooling differs widely. The IEA reports that cooling can account for about 7% of consumption in an efficient hyperscale facility and more than 30% in a less efficient enterprise data center. Climate matters, facility design matters, workload density matters, the temperature at which equipment can operate matters, so does the availability of water. Discussions about AI and water often combine several different ideas. Water may be used directly for evaporative cooling. It may be used elsewhere to generate the electricity. It may circulate in a closed loop and be reused. Consumption is not the same as withdrawal, and one facility cannot represent every facility. The careful question is not whether AI uses water. It often does, directly or indirectly. The careful question is how much, where, under what climate conditions, with what cooling technology, and what effect that use has on the local watershed. These local details matter more than a universal slogan. A data center in a cool, wet region has different options from one in a hot, dry region. A facility built beside abundant power may face different constraints from one near a crowded city. A system designed around liquid cooling may concentrate heat in a form that is easier to move, but it still requires pumps, heat exchangers, and careful leak detection. The cooling system is a second journey layered over the first. Electricity flows inward. Heat flows outward. Between them, computation briefly exists. Chapter 5: Training, Inference, and the Shape of Demand. Not all AI computation asks for electricity in the same way. Training a large model is like constructing a map through repeated adjustment. The system processes examples, measures error, and changes internal parameters. This can require many processors working together for a long period. The workload may be planned in advance and concentrated in a large cluster. Inference is the use of a trained model. When you ask a question, generate an image, or request a translation, the model is performing inference. A single simple request may be small compared with a training run, but inference happens continuously and at enormous scale. Millions of small events can eventually outweigh a smaller number of spectacular ones. There are further differences inside inference. A short classification task is not the same as producing a long response. A simple text answer is not the same as generating high-resolution video. A model that responds once is not the same as an agent that plans, searches, uses tools, checks results, and tries again. This is why a universal number for the electricity used by one AI query is usually misleading. The answer depends on model size, hardware, data center efficiency, response length, batching, software, utilization, and the type of task. It also depends on what is counted. Are we measuring only the accelerator, the complete server, cooling and power conversion, the energy used to train the model, the network, and the user's device? A number without a boundary can create an illusion of precision. The more useful lesson is comparative. According to the IEA's 2026 analysis, energy use per AI task has been falling at an extraordinary rate, by at least an order of magnitude annually in recent years for comparable tasks. Better hardware performs more work per unit of energy. Better software keeps hardware occupied, reduces precision where appropriate, reuses previous calculations, and routes easy requests to smaller models. Yet the tasks themselves are changing. Reasoning systems may spend more computation before responding. Video models generate many spatial and temporal details. Agents can remain active for much longer than a single chat exchange. The IEA notes that these workloads can require hundreds or thousands of times more energy per task than simple text generation. Both statements can be true at once. The engine becomes more efficient. The journey becomes longer. More travelers arrive. This pattern has appeared in other technologies. More efficient lighting reduced the cost of illumination, and societies used more light. More efficient engines reduced the cost of travel, and people traveled farther. Economists often call the increase in use caused by lower cost a rebound effect. It does not mean efficiency is useless. Without efficiency, total demand would be even higher. It means efficiency changes behavior as well as engineering. AI providers have a strong reason to improve efficiency. Electricity costs money. Processors are expensive. A request completed with less computation can be served more quickly and profitably. An efficient system can support more users with the same equipment. These incentives operate at several levels. A model can be distilled into a smaller one. Parameters can be represented with lower numerical precision. Frequently used information can be cached. Requests can be batched so that many users share one efficient pass through the hardware. Specialized chips can perform common operations with less energy. Workloads can be scheduled when power is cheaper or cleaner, if latency and reliability allow. Even the answer itself can be shorter. The quietest unit of energy is the one that never needs to be generated. But optimization has limits. A processor cannot be more than perfectly utilized. Memory cannot move data without energy. Cooling cannot remove heat without infrastructure. And if AI becomes useful in thousands of new settings, the volume of work may grow faster than the energy required for each piece of work falls. This is the central uncertainty in every forecast. The IEA's projection of roughly 950 terawatt-hours for data centers in 2030 is not produced by simply extending one line. It combines assumptions about equipment, utilization, construction, and demand. Change the assumptions, and the future moves. The forecast is best understood as a map of plausible pressure, not a photograph of 2030. Our unit of electricity has now completed its computational task. Somewhere, a word has been selected or an image adjusted. Yet to understand the scale of the system, we need to leave the rack and return to the grid. The rack does not consume electricity in isolation. Thousands of racks can rise and fall together. Chapter 6. When AI meets the grid. Power systems are designed around patterns. People wake in the morning, offices open, factories begin production, solar output rises with the sun, wind changes with weather, air conditioning demand climbs on hot afternoons. Operators learn these rhythms and prepare generation, storage, and transmission to meet them. AI workloads create their own rhythms. Some are steady. User-facing services receive requests throughout the day, spread across time zones. Some are scheduled. A training run can begin when a cluster is available. Some can move in time or location. Others need an immediate answer near a customer. The largest AI systems can also change power quickly. Processors move from waiting to intense work. Many machines can begin the same phase of a calculation. Training checkpoints alter activity. Failures and restarts can change load. The IEA describes large, rapid power swings as a feature that makes energy storage increasingly useful for AI facilities. Batteries respond quickly. They can smooth short peaks, support the facility during a disturbance, and reduce the stress of abrupt changes. In the right market, they may also support the wider grid. The IEA estimates that 20 to 25 gigawatts of battery storage could be installed at data centers globally by 2030. This is a possibility, not a guarantee. A battery owned to protect computing equipment may be operated conservatively. Using it for grid services requires incentives, coordination, and confidence that backup needs will still be met. The same asset can help both systems only when the rules and engineering allow it. Flexibility can also come from computation itself. Some workloads can wait. A model training job might pause during a grid emergency. Data processing could move to another region. Non-urgent work could follow periods of abundant renewable generation. But computation is not infinitely flexible. Moving work requires network capacity and available machines elsewhere. Pausing a large distributed job can waste time. Customers expect online services to respond immediately. Regulations may limit where data can be processed. And companies that have paid for expensive hardware want that hardware working. So AI can become a flexible grid resource at the edges, while its core remains a large, continuous demand. The physical connection creates another tension. Utilities plan for reliability across decades. They must decide whether a proposed load will actually be built, how quickly it will grow, and who pays for the necessary infrastructure. A data center developer wants speed. A utility wants certainty. If the developer promises a very large facility and later cancels it, other customers should not be left paying for unused equipment. If the utility waits for perfect certainty, the project may move elsewhere. Contracts, deposits, phased connections, and special tariffs become tools for sharing this risk. Local communities also enter the story. A data center may bring construction, tax revenue, and technical investment while employing fewer people after completion than a traditional factory of similar power demand. It may compete for transmission capacity, water, land, or generation. Its benefits and costs do not always reach the same people. These are not arguments for or against the facility. They are reasons to look beyond the global percentage. 3% of global electricity in 2030 would still leave 97% for everything else. But a single region can experience a much larger change. The United States Department of Energy has cited scenarios in which data centers rise from about 4% of national electricity use in 2023 to a much larger share later in the decade. Local concentration can be stronger still. The grid feels geography, not averages. A server can move a calculation across an ocean in a fraction of a second. A transmission line cannot move itself to follow. Chapter 7. Choosing the sources of AI power. If AI needs more electricity, what should generate it? The simple answer is that no single source will. The grid combines technologies with different strengths. Some are quick to build. Some can run at almost any hour. Some produce electricity without direct carbon emissions. Some store energy rather than generate it. Some are already connected, while others exist mainly in plans. Renewable energy is likely to provide a large share of growth. The IEA projects that renewables could meet about half of the increase in data center electricity demand through 2035. Solar and wind benefit from falling costs, short construction times, and contracts signed by technology companies. Their output varies, so the phrase "powered by renewable energy" can describe several arrangements. A company may buy electricity from a wind or solar project over a year while still drawing ordinary grid power at night or during calm weather. It may match demand hour by hour with a portfolio of resources. It may add batteries, or it may locate flexible work where clean electricity is currently abundant. Annual matching is useful, but hourly matching asks a harder question. What supplies the facility during every hour? Natural gas can provide controllable power and has become part of proposals for on-site generation. Developers may hope to avoid slow grid connections by building power beside the data center. But on-site generation does not remove complexity. Gas turbines have their own supply constraints. Fuel pipelines and permits are needed. Reliability may require more generating capacity than the expected load. The IEA estimates that dependable on-site gas systems could require substantial overbuilding because equipment must remain available during maintenance and failure. Nuclear power offers a different combination. It can produce large quantities of steady, low-carbon electricity. Existing plants have attracted new interest from technology companies. Developers are also exploring small modular reactors, though many designs still face engineering, regulatory, and financial steps before widespread operation. Nuclear timelines are long, but data centers may create customers willing to sign long contracts. That certainty can help finance projects. Whether new reactors arrive quickly enough to influence the current build-out remains an open question. Geothermal energy is quieter. It draws on heat beneath the ground and can produce steady electricity in suitable locations. New drilling techniques may expand the regions where it is practical. The Department of Energy has highlighted geothermal power and underground thermal storage as possible partners for data centers. Hydroelectricity already supports data centers in regions with abundant rivers and reservoirs. It can be low carbon and flexible, though new projects can have major ecological and community impacts. Existing capacity is geographically limited. Then there is storage. Batteries do not create electricity. They move it through time. Long-duration storage, pumped hydro and thermal systems may help connect variable generation with continuous digital demand. The most resilient design may combine all of these ideas. Renewable generation when available. Firm low-carbon power where practical. Storage for rapid response. Strong transmission between regions. And flexible computing that knows when waiting is acceptable. The AI industry often speaks about intelligence as though it can be scaled by adding processors. The energy system reminds us that scaling is a coordination problem. Chips, transformers, turbines, cables, cooling equipment, permits, financing, and community agreements must arrive in the correct order. Electricity is only useful to the rack if every previous step is ready. Chapter 8. Can AI help the energy system that powers it? The relationship between AI and energy is not one-directional. AI consumes electricity, but it can also help design and operate energy systems. Utilities already collect streams of data from sensors, meters, weather forecasts, and markets. Machine learning systems can help predict demand, forecast renewable generation, detect equipment problems, and identify patterns that human operators might not see quickly. A transformer can be monitored for signs of failure. A wind turbine can be inspected through images and vibration data. A building can adjust heating and cooling. A factory can schedule equipment to avoid an expensive peak. A power flow model can explore ways to use existing transmission lines more effectively. The IEA estimates that well-documented AI applications could save more than 13 exajoules of energy by 2035 if barriers to adoption are overcome. That would be roughly 3% of projected global final energy consumption. This is an informed forecast with many conditions. Software does not install itself. Sensors must exist. Organizations must change processes. Workers need training. Cybersecurity matters. An optimized system can also make an activity cheaper, encouraging more of it. AI is therefore not a machine that automatically cancels its own footprint. It is a tool whose effect depends on where and how it is used. Consider a cooling system inside a data center. AI might predict temperatures and adjust pumps or fans more efficiently. The saved energy is real. The operator may then use the available power to install more servers. Facility efficiency improves, while total facility demand remains stable or rises. At a wider scale, AI might help integrate renewable generation. Better forecasts reduce uncertainty. Improved grid monitoring reveals spare capacity. Automated controls respond faster. But a more digital grid also creates vulnerability. Systems can fail, data can be wrong, models can behave unpredictably outside their training conditions. Cyber attacks can become more capable. Human operators must understand when to trust automation and when to override it. The useful future is not a grid handed entirely to AI. It is a grid in which machines perform narrow, testable tasks, while people retain responsibility for consequences. This mirrors the data center itself. No single processor controls the entire facility. Layers of protection, monitoring, and backup surround the computation. The system is powerful because responsibilities are divided. The energy sector may use AI in the same way, as one layer among physics, markets, rules, and human judgment. Our traveling unit of electricity has become heat and dispersed into the environment, yet its path leaves a small trace. It helped a system make a prediction. Perhaps that prediction will later help another system waste less energy. The circle is not perfect, but it is real. Chapter 9. The electrical shape of intelligence. Let us return to the dark data center. Rows of racks continue working. Coolant moves through pipes. Pumps maintain pressure. Network switches pass information between machines. Outside, transformers hold their steady magnetic fields. Beyond the fence, transmission lines connect the facility to a grid that extends far beyond the horizon. This is what artificial intelligence looks like when viewed from the electrical side. It is not a mind in a box. It is a chain of physical agreements. A generator agrees to produce power. A grid agrees to carry it. A transformer agrees to change its voltage. A power shelf agrees to convert it. A bus bar agrees to distribute it. A processor agrees to turn it into operations. A cooling loop agrees to carry the heat away. When every agreement holds for a few moments, a response appears on a screen. The future scale of this system cannot be known exactly. The IEA's central projection places data center electricity demand near 950 terawatt-hours in 2030, around 3% of global electricity. Faster adoption or more intensive applications could push demand higher. Better efficiency, slower construction, or different model architectures could pull it lower. The most important uncertainty is not one number. It is the relationship between efficiency and ambition. If a task becomes 10 times more efficient and people perform 100 times more tasks, total demand rises. If models become smaller while devices perform more work locally, some demand may shift away from hyperscale facilities. If AI video becomes common, the average task may grow heavier. If agents work continuously, the boundary between one request and a long-running service may disappear. The electricity system will shape which futures are affordable. Regions with strong grids, generation, cooling resources, and equipment supply chains may attract more computing. Places with constrained power may delay projects or require new contracts. AI companies may design models around the energy available, not only around the chips they can buy. This creates a possibility that is easy to miss. Energy may become part of AI architecture. A system could route tasks according to grid conditions. It could use a small model when a large one adds little value. It could delay non-urgent work. It could expose energy or carbon settings to customers. Hardware and software could be co-designed with cooling and power systems rather than placed into a building afterward. These ideas exist in partial form today. Their future importance is an informed forecast, not a settled fact. The physical limits are not enemies of intelligence. They are the conditions that make intelligence possible. Silicon must remain within a temperature range. Current must remain within a conductor's capacity. Supply and demand must balance. Equipment must survive faults. Water, land, and materials must be managed in real places. The cloud has always touched the ground. AI simply makes the contact brighter. Closing. Tonight, we followed electricity farther than we normally do. We began at generators that turn motion, heat, and sunlight into electrical power. We crossed the grid and passed through the protected gate of a data center. We moved down into a rack, through power shelves and bus bars, toward processors and memory. We watched useful electrical work become computation, and computation become heat. We also found the paradox at the center of the story. AI tasks are becoming more efficient. AI systems are being asked to do more. The future depends on which change moves faster. There are 3 conclusions worth carrying with you. First, AI is physical. Every digital answer depends on generation, grids, power equipment, cooling, and materials. Second, global averages can hide local pressure. Data centers may remain a modest share of worldwide electricity while transforming demand in particular regions. Third, there is no single energy source or efficiency improvement that resolves the entire question. The system will be built from portfolios: cleaner generation, firm power, storage, stronger grids, flexible computing, and more efficient hardware and software. The next time an answer appears on your screen, you may imagine the machinery behind it. Not as something loud or threatening, just as a long, quiet chain. A turbine turning, a magnetic field forming inside a transformer, a current moving through copper, a pump carrying warmth away from silicon, a pattern passing through memory, and then at the very end of the chain, a few words arriving in the dark. You do not need to follow them any farther tonight. The grid will continue balancing. The coolant will continue moving. The machines will wait for the next question. And for now, you can rest.